Hello, this is Mark Unkefer. I'm director of the Fiber Optic Sensing Association, and I wanted to welcome you to our July webinar. It is Tales from the Front Lines of Fiber Optic Sensing. Our two presenters are from OptaSense, JJ Williams and Dr. Chris Minto. I just want to, as we go through the presentation, remind everybody that we will be posting these slides on our website later on the FOSA website, so you'll have an opportunity to see it at that time. JJ, Chris, we look forward to hearing your presentation.
Thank you, Mark, and hello to everyone. Thank you to FOSA for having us, and for those attending online. This OptaSense installment of the FOSA webinar series on fiber optic sensing. I'm JJ Williams, Regional Director for OptaSense out of Houston, and I'm joined by our Engineering Director, Chris Minto from the UK. Say hello, Chris.
Good day, everybody. I'm Chris Minto. Looking forward to this presentation. Thank you for taking the time to attend it.
So here's what we're going to cover today. We're going to provide real-world examples of fiber optic sensing projects and hopefully impart some of the lessons that we've learned to the benefit of your own fiber optic sensing projects. There's a lot to cover. We're going to cover a lot of different industries and applications of the technology. So we'll hope we cover your particular industry, but it won't necessarily be a deep dive into all industries. A little bit about FOSA. This is the Fiber Optic Sensing Association based out of Washington, DC. I have to say that the first few months of working as part of FOSA have been excellent. Great collaboration with other companies in our industry to share best technical practice and jointly educate the market about this technology and how to install it and so forth. There is a website, fiberopticsensing.org, which contains a lot of good information about this technology and case studies and white papers and so forth. So I encourage you to go to that to get more information. But this is a bit of background about who FOSA are. And we're joined today by the FOSA chairman, Stan Fenley from Corning. Are you there, Stan? You were going to say a few words about FOSA?
I am. Thank you, JJ. Hello, everyone. Stan Fenley from Corning. I'm chairman of the board of FOSA for 2017. I want to welcome you today as well. I'm delighted you could join us. Quick word about FOSA. This is an amazing group of companies involved in an amazing technology, and we want to help you know more about it. I'm very excited. We're launching our technology committee to facilitate installations across industries. And that committee literally has some of the greatest experts in the world in the field of fiber optic sensing, including those who are presenting today. So we're doing some good things together as an industry organization. And more than anything, we're here to help you solve your problems. For example, I know there are pipeline operators attending this webinar today. And I want to say, if you're facing situations where we can help, we want to do that. Pipelines are essential to our country. And when you have situations where people are opposing your deployments, let us help you with that. We can join you in a conversation with them, explain how working together, we can help resolve their concerns. We'd be happy to do that. I know there are telecom companies attending the webinar today. And if you need help securing your network against physical intrusion or unauthorized digging or strain on your overhead plant due to ice and snow, we can help with that. And by the way, if you want your network to double as a smart city network, we can help with that. So we're here to help you do what you need to do. Please feel free to contact us at any time. Website is fiberopticsensing.org, and there's contact information there on how to reach us. So please don't hesitate to reach out. With that, JJ, thank you very much. I'll turn back to you.
Thanks a lot, Stan. So a little bit about OptaSense. We're part of the QinetiQ group, which is around a $1 billion science and technology organization headquartered in the UK, but with probably half of our headcount in the North America region, offices around the world, and about 150 people. And we've done a number of projects for the last 10 years. in over 50 countries. So a lot of different customer requirements and a lot of different geographies and conditions to install our equipment. And talking about installations, a lot of oil and gas installations, transportation, defense and security. But as I mentioned, this has covered a lot of different customer requirements in a lot of different locations, and we're proud of the track record that we have. I'll continue. The OptaSense company is what we would call vertically integrated. So from the actual components like the laser that goes into our interrogator units, we manufacture those. We assemble the hardware, which is the interrogator unit that provides acoustic data from a fiber optic cable. And then we process that data with our software that we've developed in-house. So we have a real signal processing expertise. And then how we present that to operators. We design our own user interfaces and visualization of the software. So we do provide the full service for fiber optic sensing, and there's a lot of R&D and development that is constantly ongoing. So about fiber optic sensing, the underlying technology. So we're essentially putting a laser signal into a fiber optic cable, and then we're looking at the backscatter from the tiny imperfections in the glass. So not all of the light that we fire into the laser travels through. A little portion is reflected back, and we do some signal processing of that reflected data to look for particular signals of interest in different industries. So the talk today is focused on Rayleigh backscatter, which is what phenomenon we focus on with our sensing, but there are other fiber optic sensing technologies like temperature sensing and strain sensing. So as I mentioned, we put a pulse of light into a fiber and then look at the backscatter, and if something affects that backscatter external to the fiber, we will do some signal processing to establish what that might be and then report it to the operator in real time. Using time of flight and the speed of light, we know where that signal has come from down the fiber, and we know that to an accuracy of about 10 meters or 30 feet. So that's real-time information with a high location accuracy along the fiber. We're not putting any sensors in the fiber. The fiber itself becomes the sensor. Okay, so one of our units can do 25 miles, and apart from that, all that's in the field is the fiber optic cable, and that provides a number of benefits because you don't need in-field power and so forth. It's just the fiber as the sensor. So we use standard single-mode fiber optic cables as our sensor, and if you have two interrogator units co-located, one looking up an asset and one looking down, you can do 50 miles from a single location. So it's very cost-effective over a long distance. So our hardware provides our acoustic data, and then we have industry-specific software suites that provide data to users in different industries. So we have particular detectors and visualizations for operators in the rail industry who are looking for damage to their tracks, for example. It is going to be very different to somebody who's monitoring seismic down an oil and gas well. The oil and gas part of our business at the oil field is a service business. So we gather the data, process the data, and report the data to the operator. And our other vertical businesses are a product sale. So essentially, we are selling a product to operators in those industries, and then we often use specialized integrators who operate and are specialists in those industries. So a bit of a distinction there. So it is a platform technology. So we have the hardware, we have the software detectors, and we have the interface options. So this is an example from the pipeline industry. The number of units that we will need, and the fiber optic cable distance and so forth depends on the size of the project, and that gives us our data. That's our platform. On top of that, you have the software detectors, which are developed by us specific to a particular industry. So for the pipeline industry example, we have leak detection, which contains a number of detectors. We have right-of-way monitoring and so on and so forth. So a client can select those detectors based on their requirements. And then once we have a detection or an alarm, the way that is fed to different parts of the organization is quite flexible. We can have it at command and control. We can feed it to third-party SCADA systems, for example, to mobile crews, to their cell phones. And obviously, we can create, databases of what activity or events have occurred over a period of time. And the flexibility of the system is a benefit in terms of different information generated by the system can go to different parts of an operator's organization. So it could go to a security team for right-of-way incursions, or for leak detection, it's going to go to the central control room. And management may be interested in only specific data points. So quite flexible in terms of the data that we can look for and how we can present that data to different parts of an organization. So what does a user interface actually look like? This is an example. We have on the right-hand side what we call our histogram and waterfall. The beginning of the fiber is on the left-hand side, and distance is going out along the x-axis to the end of the fiber on the right-hand side. The blue screen here is activity over time. So it's color-coded by acoustic intensity. So if there is a activity that shows up on the right-hand side of the screen that OptaSense recognizes, it will provide an alarm on the operator's map display of their asset. In this example, we can see that there's a signal of a vehicle moving along the fiber, and the system has picked that up, recognized it, and it's generated a classified alert of a vehicle and displayed it on the map with a 10-meter accuracy. The fiber on the camera feed there is buried around 3 feet deep. Doesn't have to be exact, can be direct buried or installed in a conduit. But as you can see, we're actually picking up an individual's footsteps. So, it's very sensitive indeed. The system has recognized that particular signal of somebody walking and provided a personnel alarm on the map display. It's absolutely vital that you provide information that operators can understand, obviously. So we don't expect operators to necessarily look at the right-hand side, the raw acoustic outputs. We only expect them to look at the alert outputs, which is, could be different alerts or detectors for different industries. So that's the basic features. You can apply different performance or detectors at different zones along the fiber, which are these color-coded sections along the fiber. The south section here actually passes along a road outside this property. And if we look at this section on our acoustic readout, we can see that the south section in the middle here is actually picking up vehicles passing up and down outside this property. But we haven't alarmed because we've set the system up to say, we know that there are vehicles passing up and down. We're going to turn vehicle alerts off for that particular zone. So that's one example of how you would tailor the system to the real world. So that's the basic features, but as I say, you know, many different detectors and visualization options for different industries. And this is the basic architecture for an infrastructure monitoring system. We can scale to very large distances. As I mentioned before, it's 50 miles between equipment locations as a maximum. So in this example, we'll typically install our interrogator units in a enclosure or some kind of housing where there's power and access to the fiber. And then there's nothing really out in the field apart from the fiber itself. And we're monitoring in real time every 10 meters along that fiber. We do need to terminate the fiber, one specific fiber that we're monitoring on. And that's a key point, actually. We do monitor one fiber within a cable. The other fiber strands you can use for you know, whatever purposes you wish, so telecom and data and so forth. So we use one fiber for sensing. There's pretty flexible outputs in terms of whether we go to cameras or different locations, to SMS and to other third-party systems. We do need a network between these equipment locations, and thankfully, you know, we often have a fiber that we're able to have that network on. I will probably think of some more things to say about the architecture later. So that's a background on the software, the platform, and the architecture, and about our company. But now we're going to hear about some real installations from around the world, and I'm going to hand over to Chris.
Thank you, JJ. Well, hello again, everybody. So the title of today's talk is Tales from the Field. I've been installing systems with OptaSense since we started in early 2008, and there are many tales indeed from the field. Most of them are probably shared over a drink in the evening rather than a WebEx to potentially interesting clients. But I'm also cognizant of the fact that this is a FOSA WebEx. This isn't an OptaSense sales presentation. And so what I'm going to try and do is go through some of the isolated projects that we've worked on in the past and try and pull out what lessons we've actually learned from these deployments in the field. And this is, as Stan mentioned earlier, is a subject that's very close to FOSA's heart, and particularly to the Technology Committee. So I'm very proud to be serving on the Technology Committee. And one of the areas that we're going to be attacking as part of our initial remit of work is looking at what advice FOSA can provide as installation considerations and guidance for how to get the best out of these systems, how to consider fiber optic sensing when you're planning your assets. So I'm going to be touching on some stories we've learned, some of the good, some of the bad. There might even be some of the ugly in there. What I'm going to first hit on, though, is, if I have access, hold on, there we go. Where I'm going to first start is actually a project that hasn't reached the field yet. This is really what I want to do, is illustrate the sort of scale of projects that we may well be considering for distributed acoustic sensing. This is the TANAP pipeline. It's a new, highly strategic pipeline that is currently being built, bringing Caspian gas to Europe through Azerbaijan, Georgia, Turkey, and then onwards into Greece and ultimately to Italy through some other connecting pipelines. TANAP is the section in Turkey that we're interested in. And OptaSense is very pleased to have been selected to provide both the security system around the block valves, sensing intruders, trying to either climb the fences or walking up towards the block valve stations, 64 systems, one at each block valve site, but also as the main pipeline protection system and leak detection system over the whole 1,100 miles of gas pipeline. It's an absolutely amazing project, and it covers a country. And so when we're thinking about the deployment of systems, as a client, perhaps as a front-end engineering design consultant, is looking to see how you can establish value out of your fiber optics that you may have along your asset for different purposes. In this case, there was going to be multiple fiber optic cables. So by just thinking about where we position those cables, we can bring out different applications. So if the fiber is way out at the side of the right of way, it doesn't really have much to offer in terms of the ability to monitor the pipeline for background intrusions from accidental damage. But if we work at the early stages in design, work with the contractors for the build of the pipeline, it's possible to then plan out the location of the cable to give a whole load of additional value that can be realized from a sensor that you already own. If you put it in the wrong place, it's got no value as a sensor. But by thinking carefully where the location goes, not interrupting the workflow for build, you can get 1,100 miles of sensing in this particular case. Scope here also includes one of the very long crossings underwater for fiber optic sensing, the 30-kilometer, almost 20 miles of crossing of the Dardanelles Straits. All of the each job brings its own challenges, and that's one thing to consider when you're planning out your work. You may have a well-designed workflow, but every job is unique, and we have to be able to customize the end result to the client. And in this case, the application demanded a new architecture, moving to a fully distributed architecture to remove any single points of failure. There are now none in the system at all or in the interfaces, and being able to offer a brand new way of sensing for leaks in the underwater section, which I'll touch on a little bit later. But we're very proud to be part of this project. It's got through its factory acceptance test, and it's in early stages of being deployed in country. Turning to the South Americas, the Bicentennial pipeline in Colombia. This is a project we worked on, started in 2014, and we worked on this for a few years. Its main purpose was counter intrusion, particularly attempts to damage the pipeline from local terrorism activities. And we have turned up, we've deployed our system on the existing fiber that the client already had in place. We're able to put in place the algorithms that John talked about earlier to provide that level of protection on the pipeline. Everything comes as a surprise. Every new job brings some environmental knowledge. In this case, it was cattle. We'd already developed a cattle filter for some additional other projects, such as particularly with camels in Kazakhstan, seemed to cause a bit of a problem. But the sound of cattle's feet moving can sound a little bit like the impact of a spade on the ground. And if you don't plan for that, it can confuse your detectors. In this case, we had massive herds of cattle that were flooding the environment of the pipeline and potentially obscuring the sorts of digging activity that we were trying to detect for the client. And so we developed instead a cattle herd detector to be able to not obscure the message that was going through to the client's operators and be able to try and focus down on the alert. So for our operators, nuisance alarms are absolutely key. And the efficacy of the system comes down to how well we can distinguish the benign background activities from the absolutely key things that we're trying to detect. And for us, we work with clients at an early stage to put in place what we call a threat profile. So the clients will tell us exactly how they want the system to operate. That all works well if the clients know how the system to operate, but we can generally help out. Totally different example. So in Mexico, we have refined product pipelines that are crossing the country, and the clients knew that they were being plagued by attempts to steal the product. And the question is, OptaSense, can you come and do anything? It's an LPG pipeline. There was an existing communications fiber running parallel to the pipeline. We felt there probably was something we could do by repurposing existing detectors that we already had. And we brought our system to bear. And what we found is as soon as anyone opens their illicit hot taps, we can see the product escaping. And what it generates is these V-shaped chevrons that you can see on the video. These are negative pressure pulses, shock waves that go both upstream and downstream through the fluid as a result of the difference in density between inside the pipeline and suddenly being open to the outside world. That's a very strong indicator of a leak. It's then partnered with orifice noise as the fluid bubbles out of the pipeline, constrained in the thief's hose. So the clients knew they had, by the use of mass balance, for example, they knew they were having leaks. The problem is they just didn't know where. So this is one of the advantages of fiber sensing, is that with measurement sensors every 10 meters, every 30 feet, we can pinpoint it. So we located the hot taps. The next problem, of course, is the local environment and conditions. You now know you've got a leak in your pipeline. You have to do something about it, but it's not a safe place to operate. That's not something we can do, we can necessarily help with, but we can certainly help clients focus on what the next actions may well be. So this is an example of how a leak appears in a pipeline. I mentioned there were a couple of different signatures that we used. There's actually 4. We utilize negative pressure pulse. You can see an example here of a man-made leak occurring on a pipeline. So this is essentially using a valve on the pipeline itself. Time runs vertically. So here the newest time is at the top, the oldest time at the bottom. When you open the valve, you see orifice noise as the fluid is leaving the pipeline. That's one of our detectors. When you shut the valve, you can see the negative pressure pulse, again, from that change in density. We have 2 other detectors that we use to provide a full integrated leak detection approach, measuring the environmental strain from fluid leaking into the soil. And we can also do some element of measuring the temperature change caused by that leak itself. We integrate all of them into a single leak fusion package. So another project, Yemen LNG. This is a really good example of how systems can help. In this case, it was a very austere environment, a lot of counterterrorism work going on. The pipeline had interruptions on a monthly basis. People were bombing it, Al-Qaeda in the Arab Peninsula. Lots of exciting stories from that project. We came along, we implemented our system. The attempts on the pipeline dropped to 0. Absolutely fantastic. The downside is you can maybe block off some approaches to terrorists if that's what you're trying to do, but it may then open up work into other avenues. So as soon as the route to do damage the pipeline was shut, terrorists turned their attention to other areas of the overall infrastructure. But from the perspective of protecting the pipeline, the system has done its job very well indeed. Similarly, in Turkey, as a precursor to the TANAP project, we've been working with the BTC Pipeline since 2009, one of our earliest installations, one in which we really learned how to deploy systems, learning about how the local environment changes along the pipeline, how to calibrate our systems to be able to cope with those changes. The overall performance is a mixture of how well the fiber performs, what the local ground type is, and what your system can do. We need to be able to calibrate for those changes along the pipeline. And as a result of our early projects where we found out how hard that was, we then went off to develop our calibration tool to use as part of these projects. Some of what is most exciting about projects is the data that comes and surprises you. In working on the BTC pipeline in those very early days, we didn't perhaps have the solid-state lasers that John mentioned at the beginning, part of Redfern integrated optics, which we now use as our standard. And they're very much the sort of standard lasers to use for fiber optic sensing. We had some more fragile experimental devices, and I was always wary of systems falling over and starting to get spikes in the data. On one day, I happened to start seeing these spikes coming in from the right-hand side, pretty much as we're looking at now. It's a slightly cleaner picture of it. Thinking the system was going on, starting to fall apart, which was going to embarrass me in front of my clients. And then as I carried on watching, it appeared it had structure. It had a speed, which we are plotting here, distance, and we're plotting time. So the angle of these V's is a speed. Things don't travel along that are problems in your system. They appear as instant spikes. And so with this, by simply watching the anomalies, trying to work out what they may be, this has been a technique we've used on many, many projects. And in this case, what we discovered was, by just speaking to the pipeline operators, we were monitoring a cleaning pig going along the pipeline on its weekly run. And then suddenly we'd moved from being there to prevent hot taps to suddenly having an operational tool to monitor the location of their pigs, be able to inform them when they were closing in on the pig capture station. And on other pipelines, not on this one, we've also used it to help locate stuck pigs and help unstick them as well. So moving on, one of the other opportunistic pieces of data, again, negative pressure pulses in the pipeline. They're so important, they're there, and they can travel for many, many miles down a pipeline. In this particular case, I'm looking at a section of pipeline where there's a really steep drop. The elevation of the pipeline drops rapidly. It's an oil-filled pipeline. We start to get some column separation in the pipeline. We have slack lines, and that creates massive shock waves. And on an above-ground pipeline, that can shake the system apart. For us, this causes loads of interesting engineering challenges in working around that dynamic environment and still being able to deliver the product to client is one thing. But on the upside, you then suddenly got a tool to be able to monitor the extent of the slackline work. It varies very much with the flow conditions of the pipeline, and generally, people don't know to what extent the shock waves will travel because there's no real means of measuring it. With a DAS system, as well as doing your normal job of working with the acoustics, we've found we've been able to use this to monitor the extent of slack lines, which then tie into the flow conditions very successfully. So we don't just stick to land, and we don't just stick to oil and gas. I'm going to move off oil and gas in a second, but just as a slight aside, we also have a very extensive business going on in downhole oil and gas, where we cover a full range of downhole products that can be delivered in parallel, fracking, flow monitoring, and in this case, VSP. This is one of the, we believe, the very first deep sea VSP, vertical seismic profiling capture exercises. We started it in 2012. Key thing here is, with a fiber in the well, you can come along anytime and carry out your reservoir analysis by doing your seismic profiling. Whereas in conventional approaches, you'll put down an ocean bottom cable, and every time you want to come, you have to bring your cable down, lift it back up, hope it's in the same position. If you've got a fiber in the well, you just turn up whenever you want, fire off your seismic signal, and you can instantly image the reservoir to give you enhanced abilities for oil recovery. Down at the bottom left picture, we see essentially a time-lapse comparison image showing how the reservoir has changed over time. We've been revisiting this project for about 5 years now. A very exciting new capability that makes oil recovery a much cheaper process. So moving away from oil and gas, as John mentioned earlier, we do a lot of work in road and rail as well. And here's just a couple of areas where we've had some excitement in the rail industry. So we work across 3 different pillars. We do safety and security, helping people prevent copper theft, for example. We'll do asset condition monitoring, either of the moving assets, trains themselves, but also of the track. And we'll also monitor train movements. We don't have an enhanced safety integrity level, but we can certainly act as a component of a wider system. 2 examples here of different sets of data or activities that have taken place. The video on the bottom left is from a North American canyon where we were employed to do rockfall. And this is illustrating one of our calibration drops. So again, with the concept of environmental calibration, mapping where the fiber is in relation to your asset. We're not protecting the fiber all the time, we're generally protecting the asset. Normally it's an engineer walking along with a weight drop tool. That's nothing like a rock. So in this case, we take a grating approach, and every few miles we'll turn up with a 500-pound weight and drop that off a mobile crane and use that to calibrate the sensitivity of our system. We also learned in that job that with a passing standard candle approach of the train itself, we can utilize that to understand the offset of the fiber from the train, and also the soil conditions that might be between the two, and use that itself. So sometimes the work surprises you and you get given free assets with data that you can then make use of. Equally, we've tried similar projects out on other railroads, but fiber has just been too far away to be able to make use. So understanding your limits and being able to get those concepts across to the client and be able to understand and project those limits to the client's project before you start is absolutely critical. We're always very believe in understating our abilities so that we're never interested in the clients being disappointed. Moving on. This is an example of railroad theft where we were working with a client in the UK, both to detect intruders on the track, but also to then be able to discriminate between someone trying to steal the copper cables that were powering the cranes and the background activity. We utilized this work during part of the London Underground deployments for the London Olympics a few years ago now in 2012. And even during that short period the system was mobilized, we did indeed detect attempts on the infrastructure of the London Underground. Quite amazing. We also work in smart roads. We've currently got a major project that we're deployed with Cisco in the Netherlands, Cisco Systems, working on smart road infrastructure, where with a fiber embedded in the road or at the side of the road, we can monitor the passing traffic, we can look at the traffic flow, we can look at the journey times, and we can look at detecting any incidents that arise. And again, we can utilize the passing traffic as part of our calibration process, help guide the system towards operational performance. A lot of our work has been traveling around the world, replacing existing systems that perhaps don't perform so well. Detecting is one thing, and as I've mentioned, detecting with a good nuisance alarm rate is another thing altogether. And I think one of the challenges that fiber optics sensing brings to the marketplace is being able for people to discriminate. There aren't really any standards of interrogator units or of standards of performance of system. And I think it's very difficult for clients to be able to discriminate. It's all lumped in under fiber optic sensing or distributed acoustic sensing. And so I would say that from this perspective, for clients to be able to accurately write down their requirements and test people against them is absolutely essential. We've done a number of jobs where we've replaced earlier generations of perimeter intruder systems, which have generally been turned off because wind noise, for example, has raised too many nuisance alarms. With OptaSense, we don't have to just wait for the fence to be shaken. We can actually listen to the fence and hear the disturbances and discriminate that from the wind noise. So we've done that very successfully around the world. Moving on, because I'm cognizant we're running out of time a little bit, so moving forwards. Also, jobs will surprise you. We mentioned railroad jobs. We've done a number of railroad jobs. As it happens in the Bay Area, there was a major telecoms outage a couple of years ago. We just happened to be monitoring it. We caught the whole of the event. We could see the unusual activity leading up to the event. We could see the vandals coming into the location where the fibers come in, and we're able to spot the activity and then ultimately see the cut of the fiber. We carried on operating up to the cut, but things like this, again, they expose different levels of ability. You may be there to monitor trains, but who else can make use of your data? And we've yet to see fiber providers get together with other asset owners, but I think that's part of the future. Again, in a similar way, you can use your systems to measure earthquakes. One of the early jobs that we did, we started seeing earthquakes coming in, and again, it's, my God, what is going on with your system? The careful analysis showed that we were actually doing a very good job of measuring seismic activity. And again, I think we now work with Stanford University and the Stanford Exploration Project for some of this. And I think, again, there's a future potentially for many asset owners to exploit the data that they're recording. So they're using their system for leak detection or intrusion monitoring. There potentially is other applications of that data where there may be further users who may want to exploit some of it. And in this case, we can use the fact that we have a distributed system with many, many sensors to actually carefully plot out the epicenter of any seismic activity. Similarly, in rock and rail, continuing with the seismic theme, we work on measuring rock slides. We alert against rocks, as we saw earlier, and some data there to show that that indeed has been successful. Again, other places that you may have fiber that people don't think of. The optical ground wire in overhead electrical pylons will generally have fiber in those. I'm just trying to see if we can make that play. It may not. What we found is that with the fiber just running along the top of electrical power utilities, we can pick up intrusion events at the bottom. So again, utilizing opportunistic data. So chap there just hitting the pylon with a hammer lightly, we can pick that up from the fiber optic that's on the surface, that's on the very top of the pylon, and provide an alert and provide an instant location of any attempts to intrude. And sadly, in many places, the metal in the pylons becomes a target for thieves. And so using OptaSense, we've been able to help monitor the integrity of the electrical infrastructure, which of course then becomes so important to so many people. In a similar vein, in subsea, we help locate failures on power cables. And again, utilizing data of opportunity, vessels tracking over the cable, once you've found the location of a break, in this case, it's been activated by a short circuit device, can't send our engineers out to go and walk along the cable to find it, but we can send a boat out along top, match up the channels, and then within maybe 30 to 50 feet, be able to pinpoint electrical failures. So I'm going to hand back to John at this point, who's going to wrap up.
Thank you very much, Chris. And I'm going to try not to become too preachy here in terms of the lessons that we've learned, but cover some of the points that we feel are key in terms of having a successful fiber optic sensing project, and try and impart that for the benefit of all on the line, including with some horrendous stock photos. So from a lessons learned standpoint, from a design and engineering standpoint, we would always recommend that engineers and designers engage with the market early about the project. This is not a commodity product or technology. You can't just order 2 DAS and then be away. You need to get involved with the supply chain, talk to people about exactly what is needed for a particular project. Cable installation and design is slightly different than telecom, so get help with that. There's plenty of good consultants and sources of information, because the cable installation for sensing is going to be slightly different. And often a project can provide value to other business units within the same organization. So IT groups, for example, love fiber because it gives them access to high data rates for over decades. There's a task ongoing at the moment with the FOSA technical committee in terms of best practice for designing and installing fiber optic cables for sensing. So we're going to provide some guidance to the industry or for best practice for different applications and technology types. For construction, we would say there's plenty of good experienced contractors and systems out there for installing fiber. We would say that scheduling is important. So if you have multiple contractors, make sure that the interface management between them is and communication is strong, and that one contractor isn't getting in the way of the other. The use of a conduit can often help with that, because you can blow the fiber after a particular asset has been installed. And if you do have dialogue during design, engineering, and construction, that helps with the trade-offs that are always present with a cable installation for sensing. So we may have optimal locations or positions for the fiber that we would like, but we always understand that it's a trade-off between what's perfect for us and what's practical from a construction standpoint. So that's normal, and good communication should be had on where to install your cable and how to install your cable. For installation and commissioning, we would say that planning is important, of course. We have a very robust step-by-step process, and that's a repeatable kind of project management process for installing fiber optic sensing systems. Health and safety is obviously vital, so a robust health and safety plan is always recommended. We will set the system up with detectors that are available out of the box, if you will, but we can't predict what environmental activity there will be along a particular asset. So when we install a system, we need some time to understand the asset's environment and then adjust the detectors accordingly. So the good thing is that nearly all of that can be done remotely. So it's not too onerous a process, but it does need to be considered in terms of fine-tuning a system. And I would say that clear scope and requirements are very important for commissioning in terms of aligning expectations of all parties with a clear dialogue ahead of time. So, we have done some projects where client hasn't really assessed what they actually want. So it's always important to establish goals and actions ahead of time for a monitoring system. And then for operations and maintenance, we would say that these systems create a huge amount of data. We do a lot of signal processing to boil that down to actionable data. But in terms of system requirements, it's always sensible to focus on what do we actually need to know, and when do we need to know it, and who needs to know it. We would say that training has a high return on investment. We have various courses available, so we understand that companies have personnel changes, time passes by, and additional training of the best way to manage the system may be required. And we also, really advise that operators think about how will this fiber optic sensing system fit within a wider management and control architecture. So what other third-party systems, front ends, do we need to consider when using this fiber optic sensing system? And while this is an extremely powerful technology and system, it's only going to work if it's the data is actioned on. So we always encourage operators to establish protocols for operation. What do we do if we get an alarm? Now, OptaSense can advise and provide feedback on what is done on other projects in other parts of the world, but really it's up to an operator to establish the best protocols for their internal management systems. Okay, so that takes us up to 10 minutes left for questions, and if I can just provide a summary for what we've learned, we would say that planning is key. Using experienced contractors, not waiting to the last minute for design or engineering or even installation, following process, getting budgets established early and clearly, and engagement with the market to get input on how projects should be done. Communication, don't wait to the last minute again. Early communication is always good. Be proactive. Project management is important, and support. Use the support tools that vendors provide to keep communicating with them. And then, of course, health and safety is an absolutely vital part of these kind of system implementations. So make sure that all health and safety plans are in place and measured and reported with a robust process. So that concludes our slides, and I think we'll pass back to Mark to see if there's any questions from our audience.
Sure, thank you. And let me first briefly explain what the process is. To ask a question, there's a text box to the right on your GoToMeeting interface that will let you type in a question that I'll be able to pass on. If we're not able to get to it, I know that both Chris and JJ are willing to kind of respond to questions that we get afterwards. So even if you got an idea, come in late, feel free to ask a question. I'm struck one of the first ones was one really responded to something that I noticed. I think one of the things that the videos show is really kind of makes it possible to visualize in a real understandable way how fiber optic sensing works, and you can kind of see the interaction between the real world and how the technology. So the question was, when will these videos be available, or will they be available? And the short answer is they will be. We'll have them posted on an on-demand basis on FOSA's website in about 24 to 48 hours, and we'll be keeping that up indefinitely. So there's an opportunity to take a look at that in a little bit more detail. I also, just so I don't forget, remind that we won't have a webinar in August, but we have the next one coming up on September 20th with FOTEC. I just want to kind of touch on one question in seeing kind of, there's almost, as I understand, almost a visualize an art to being able to read or detect or discern what folks are seeing, what signals are being, what threats or what non-threats are being detected. I wondered if you could give a little bit more color as to whether or not it's necessary to rely on OptaSense, or can other folks be able to write algorithms for the DAS, for the data that comes out of a DAS unit.
Chris, do you want to take that?
Yeah, certainly. Yeah, so we're from OptaSense, and as John mentioned at the beginning, we're sort of vertically integrated and set up to do that. So the natural answer is, oh yeah, you definitely need OptaSense. But we do recognize that there are many occasions where other expertise may well be available that clients wish to use their own, and we do have an architecture that supports plug-in algorithms, for example. The sort of places you can go to for algorithm development are fairly limited. They tend to be people who are used to dealing with thousands of channels of acoustic data, and for that, the really only place you can go to is submarine sonar research, and most of the capability that has come out in DAS, at least in the early years, has been in some way connected back to those old sort of military institutions who have done it, our own included. Most of our engineers have got some background in sonar system, either sonar design itself or sonar equipment processing. But we do have a few examples of work that we have done where clients have brought in third-party algorithms that they've developed themselves. And although I wouldn't say it's very common, and for a client who's implementing it, they must probably have a fairly clear desire to want to use something other than what comes out of the box with its own performance guarantees, etc.
Here's another question that I've heard before, so I'll jump on it, which is, how close does the fiber need to be to a pipeline for pressure pulse detection?
So yeah, many of the examples that I've shown there, for example, the pinging, that is a signal that is pressure pulse in origin, slightly different one from a leak. But that signal will pass through the ground close to the pipe. You'll have a very wide frequency range. Further away from the pipe, the high frequencies get absorbed in the soil, and you'll have less and less to work with. But we've utilized pressure pulse signals in the ground from over a meter, 3 feet or so away from the pipeline. Normally for leak detection purposes, we would advise to get the fiber as close as you can. The closer the better, but typically about a foot away to get the maximum leak size performance. But for pinging and from some of those other activities, the counter theft, for example, 3 feet or potentially more is possible. It'll also all depend on the fiber itself, the soil type in between the two, but we'll publish advice on that.
Sure. And here's one from somebody who says they're with an electric utility. They wanted to know if the solution to detect high temperature of underground high voltage cable, and if there was any particular type of fiber that was necessary for using for that kind of use case.
So the type of fiber, they're all made of silicon, they're all made of glass, so they'll have a responsiveness to the temperature that is a characteristic of the glass itself. So it's a little bit less to do with the design of the fiber, but more in that case you would consider really the design of the cable itself, and the dependency is really more to do with whether it's single mode or multi-mode and how far down the cable as a result you would want to be able to look. So we would, in the case of failure, really be looking at the acoustic signal rather than perhaps the temperature signal, although we can perhaps do some monitoring there with our temperature gradient. There are other systems, distributed temperature monitoring systems, which can be quite good at looking at the temperature surges in cables. But as I say, there's a range of different signatures that might be available.
Next question deals with sort of short distance versus long distance, and kind of made the case, I guess, that looks good for using a monitoring infrastructure at, say, 50-mile range. The question is, are there advantages or are there use cases associated with shorter systems in sort of in the order of less than a mile?
Yeah, so the shorter that you make your fiber, the quicker you can repeat your sampling. So the higher frequency range that you can monitor, the brighter you can make the signal. You can do more and more as you get to shorter and shorter systems. So a lot of our downhole work, surface seismic, vertical seismic, fracking, etc., that's typically 1 to 3 miles. Perimeter security will generally be 1 to 3 miles. Condition monitoring can be very localized down to sort of plant level. There's a variety of applications, and essentially wherever you may have a vibration component that you're interested in monitoring and you have a fiber, then we can generally pool the two together to do some quite special discrimination of signals and try and pull out what parts of the industrial process are of interest to you. And at these smaller scales, it's generally either a small scale security interest or perhaps an industrial process. So conveyor belts, for example, are another good example where there's a very complex acoustic environment. There's a lot going on. Can we use acoustic sensing to look for the squeaky bearing, that type of activity?
The next question follows up a little on that, is kind of asking for, are there examples of the sort of large-scale large-scale perimeter or border projects where cable has been used, fiber sensing has been used for detection?
Yeah, so there's certainly with border projects, there is quite a number of borders around the world that OptaSense is instrumented on. Can't always talk about where they are and what they're doing because they can be quite sort of sensitive and client confidentiality becomes an issue. But certainly, for border monitoring of sort of traffic that is going across for smuggling purposes, that is quite common. Counter-terrorism purposes is also quite common. You've got the potential for the use of fiber as an invisible border. So being able to monitor what is going on in a border environment without putting up barriers that can upset the flow of animals or the flow of nomadic people, for example, you still have a means of tracking and monitoring activity and looking for anomalous works. So as an additional part of that, some countries may be planning large-scale border deployments of surveillance equipment. The problem is, until they approach the project, they don't really know where their activity happens to then be able to plan on how best to deploy their equipment. So that's, again, another use of distributed acoustic sensing, is that economically, it's quite a cheap process to consider deploying on a border. Now, when I say quite a cheap process, I mean in comparison to putting radars and cameras everywhere. So what DAS can then be used is to build up the pattern of life. What are the daily occurrences? What are the anomalies? Where do you see activity that you weren't expecting to? And this has been one of the constant themes of deployment of DAS. People get very excited about it. They want to know everything that's going on. Once you start to put DAS onto your asset, generally the biggest response from people is shock that I didn't realize there was that much going on. People generally have an idea in their head that there are pipelines or their borders or their assets are quite quiet places. We come along and put the microphones everywhere. Suddenly they find out what is quiet and what's not. And that really changes the operational picture and the question you ask of the system. John, do you want to add anything about border applications?
I think you've covered it well. Just regarding perimeters, we do have a good fit for large sites, airports, nuclear stations, high-value residences, properties, refineries, electrical plants, utilities sites. The system can be buried or it can be fence-mounted. In terms of the question of what's the biggest, perimeters can be 10 kilometers to up to 20 kilometers, not normally much longer than that, often a lot shorter. And for borders, the biggest, I think on the order of hundreds of miles rather than thousands, although it is, of course, possible to install systems above 1,000 miles in distance.
Next question is probably a nice segue off of what you just said, which is the question is while every installation is different, what's the approximate cost of the system outside the fiber and fiber construction costs?
Sure, yeah. Just as this is a public forum, I'm not going to get into pricing right now, but if I think it was Matthew who asked the question, if he would like to send me an email, then I'd be delighted to begin a dialogue with him.
Sounds good. I think that's our last question, although as I mentioned before, both JJ and Chris are available to respond to questions offline and perhaps maybe be able to give a more detailed response. Again, I want to remind everybody we have our next webinar coming up in September. I'm looking forward to that. And this one will be available online as a resource at the FOSA website. Thank you all for participating, and thank you, JJ and Chris, for a very informative presentation.
Thanks to all. Thank you.
Thank you very much for attending.